Okay, so let's complete the proof of the cyclic decomposition theorem. Cyclic decomposition theorem. In the previous lecture, we had discussed the first half of the cyclic decomposition theorem. Namely, we had broken down the proof into 4 steps. We had done the first 2 steps in the previous lecture, and we are going to complete the proof in this very lecture. Let us quickly recall what the cyclic decomposition theorem said, and then we will just quickly be revising the facts which we had already done about this theorem. So let's talk about the statement first. The statement was that let T be a linear operator. Let T be a linear operator on a finite dimensional vector space V, let's say over the field F, and let W naught be a proper T admissible subspace of V. Okay. Then there exists non-zero vectors, which were named as alpha 1, alpha 2, alpha r, and respective T annihilators which we named as P1, P2, Pr, such that the following holds. So number one, that V is a direct sum decomposition of W naught and the T cyclic subspaces generated by all of these non-zero vectors. Okay. Then you have here Z alpha R P, and number two, we have that Pk divides Pk minus 1 for all k ranging from 2 to R. Furthermore, we had a statement about uniqueness that further the integer R and the annihilators P1, P2 till Pr are uniquely determined by 1, 2 and the fact that no alpha k is 0. Okay, so this was the statement of the cyclic decomposition theorem, and what we had already proved. Okay, so we had proved the following steps. So let me just say already proved. So we had proved the following statement. Statement number one was of this form, that there exists non-zero vectors which we said as beta 1, beta 2 till beta r V, obviously, such that V is a sum of W naught and the T cyclic subspace generated by these vectors. Okay, so Z beta 1 T and so on till Z beta R. Observe that this wasn't a direct sum, this was a simple sum. So this was the substatement, and another substatement was that if we have an index k within the range 1 to R, then we have the structure of the subspace Wk, or we should write it as like, and Wk was W naught plus Z beta 1 T, so on till Z beta k T. Then the T conductor of beta k into Wk minus 1, which is given as say Pk, SBK WK minus 1, this notation which we had used in the previous lecture, has maximum degree, or I should write it such that the degree of PK is the maximum degree of all the T conductors into WK minus 1. Okay, so maximum among all vectors. Yeah. Okay. This is what we had proved in step 1, right? Okay. Then what we had shown in step 2, we had shown in step 2 that let beta 1, beta 2 till beta r be vectors which obey 1 and 2 of 1, right? Of 1 of this point, this step 1. Okay. We fix a k is within the range 1 to r. Let us choose a vector beta from P, and let f be the T conductor of beta into Wk minus 1. Okay, it's the T conductor of beta into Wk minus 1. If the image of beta under the operator ft is written as some beta naught plus summation over 1 less than equals to I less than equals to k minus 1. Okay, and here we have some polynomial gi with t acting on bi, but each bi is in wi, beta naught is in w naught, beta 1 is in w1, and so on and so forth. Then the T conductor of beta into Wk minus 1 must divide each of these polynomials gi. This should happen for all I, and there exists an element gamma naught from W naught such that Ft of gamma naught is equals to beta naught. Okay, this was our second step. Okay, so we will obviously be using these steps for sure. That was the main reason why we had these statements. But before moving on to step 3, let me just recall one more observation which we had. Okay, so actually we want to see when does a subspace W and a certain T cyclic subspace are independent. Okay, that is our goal. Okay. So what I'm trying to say is basically, one sec. Okay, what I'm trying to say is basically that suppose W is a proper T invariant subspace. Okay, this observation we had already covered in the previous lectures. Okay? So let W be a T invariant subspace, a T invariant proper subspace, a T invariant proper subspace of V. V is assumably finite dimensional. Okay, we want to find a vector. Okay, we want to find a vector alpha such that W intersection T cyclic subspace generated by alpha is zero. Is a zero subspace. Okay. T is obviously a linear operator defined on V. Okay. So how do we do this? What we do is that we choose a vector beta which is not from W. Let beta be not in W. Okay. We consider the T conductor of beta into W. Let F be the T conductor of beta into W. Okay. So this is small s. Okay. We have two notations. The capital S beta W. This represents the whole ideal. The ideal, which we call as the T conductor, and this is the unique monic generator of the ideal. Okay. So F is the smallest beta W, the T conductor of beta into W. So obviously that means Ft of beta is in W. Okay. Now what we do is that suppose W is T admissible. Let W be T admissible. T admissible. Then since Ft of beta is an element of W, so by the definition of the admissibility, there exists some element gamma in W such that Ft of beta is equal to Ft of gamma. Okay, is it clear? We choose the vector alpha to be beta minus gamma. Okay. Now obviously gamma is in W, so that means beta minus alpha is in W. Right? So if beta minus alpha is in W, then what does that mean? So this means that GT beta is in W if and only if GT alpha is in W. Simple structure of what a vector space is, right? You can also think of it as the closedness property of a vector space, vector subspace or vector space, whatever. So what does this typically mean? This means that the T conductor of beta into W is same as the T conductor uh, of alpha into W, right? Okay. But Ft of alpha is 0, right? This is obvious from here because Ft of beta is equal to Ft of gamma. So Ft of alpha is 0. So if Ft of alpha is 0, then this F becomes the T annihilator of alpha. So this implies F is the T annihilator of alpha. Because obviously it is the least degree monic polynomial such that this happens. So it's the T annihilator of alpha. Moreover, what is the other observation, which is the another important observation we have? We have that if GT beta is inside W, if and only if GT alpha is inside W, so that means GT of alpha is inside W, if and only if GT of alpha is 0. Because Ft of alpha is 0, F is the T annihilator, F should obviously divide G. So, or you can think of it, F is the T conductor of alpha into W, GT alpha is inside W, so F should obviously divide G. F annihilates alpha under T, so therefore G will also annihilate alpha under T. Right? So GT of alpha is equal to T. So these two are the important observations. Okay. Okay. So now let's come to the proof of step 3. Okay. Step. What are we going to prove in step 3? We are simply going to prove that there exist non-zero vectors, R non-zero vectors, alpha 1, alpha 2 till alpha R, such that the cyclic decomposition theorem holds. That is what we are actually going to do. Okay. So on the step 3 we show that there exists non-zero vectors, or I can simply say that I can simply say it like this, that there exists vectors um, such that the cyclic decomposition theorem holds. Such that the cyclic decomposition theorem holds. Okay. Okay. Now observe first thing first, that in step 1 what we had shown that there exists R non-zero vectors. Okay, let me frame it in this form. Okay. So yeah, we had already shown that. Let me just change the color. Yeah, we had already shown that V can be written as W naught plus Z beta 1 T and so on till Z beta R. We have such vectors. So there exists vectors beta 1 till beta R such that this happens. Okay. The only thing which we need to impose on this structure is the concept of a direct. In other words, we just need to show that the subspaces are independent. Now recall we had the subspace structure of Wk minus 1 of this form. So it was like W naught plus Z beta 1 T and so on till Z beta K minus 1 T. If I show that Wk minus 1 intersection some cyclic subspace, let's say alpha k, is equal to 0 for all k which is in the range this, then these vectors alpha 1, alpha 2 till alpha r are such that V is a direct sum, right? Because of this independence, we need to find out these alpha k's only, and finding out these alpha k's is somewhat a more concrete structure of the observation we had. So this makes this a direct sum, and so on. Well, Z alpha R. Clear? Clear? Okay. So yeah, so our goal is to basically use step one, use the vectors in step one to find out these vectors such that this statement holds. Okay? That is what we actually need to do. So let's start with the proof. So we start with the vectors beta 1, beta 2 till beta r in step 1. We fix k is in the range r to 1 to r. We apply step 2, we apply the statement of step 2, we apply the statement of step 2 on the vector beta, which we have chosen a arbitrary vector beta from V as beta k, and in the step 1 we had defined the T conductor of beta k into Wk minus 1 to be having the notation Pk, I guess, right? So we choose the T conductor and F equal to Pk, because if you recall in the first statement, let me just, yeah, so here F was the T conductor of beta into Wk minus 1. In step 2 we had denoted that Pk is the T conductor of beta k into Wk minus 1. So we just replace F by Pk and we replace beta by beta k in this very step, in step 2. Okay. So F equal to Pk. What do we obtain? So we already had a direct sum decomposition. What was the structure of Wk? Beta k is an element from Wk, right? So the structure of K minus 1 was some sort of a, so let me just write it as Wk, right? So Wk was a sum till, so Wk was given as W naught plus Z beta 1 T, so on and so forth, till Z, yeah, what we had, Z alpha, Z beta kt. What we can do here is that we can typically use this notation that we obtain. So from step 2, we obtain Pkt of beta k can be written as some Pkt of gamma naught plus summation over 1 less than equals to I less than k Pkt times some Hit of beta. Is it clear? Okay. Where Hits are certain polynomials. Okay. Hits are certain polynomials. So let me just write it down here. His are polynomials, and gamma naught is in W. Okay, clear? Yeah. So we have this. Okay. Then what we do? We choose a vector alpha k. Okay. Let alpha k be given as gamma naught, or let's say beta k minus gamma naught minus summation over 1 less than equals to I less than k Hit of beta I. Okay, we do this. Then now obviously, so that implies beta k minus alpha k is in wk minus 1, right? We kind of consider this structure, nothing else, from the way wk is defined. So we consider this structure, and then we assume alpha k a vector which is defined like this. So then we have that beta k minus alpha k is in wk minus 1, clearly because of the structure of wk minus 1. So, so see, each of these elements are from the T cyclic subspace generated by beta I. It ranges up till the T cyclic subspace generated by beta k minus 1. And gamma naught is an element from W naught. So this part is completely inside, or rather I should say, not exactly this part. This part is completely inside wk minus 1. So alpha k, so beta k minus alpha k is clearly inside wk minus 1. Right? That's all. So, so that implies, so the observation we had, so that implies the T conductor of beta k into wk minus 1. This must be equal to the T conductor of alpha k into wk minus 1. Okay. The T conductor of beta k into wk minus 1 was noted as pk, so we can write this as pk. Right? But pkt of alpha k is 0, clearly because pkt of beta k is of this form. So if you apply pkt, so suppose this is star, so if you apply pkt on stars, the right hand side becomes 0, right? Is it clear? Yeah, one second. Yes, as I was saying that it, so the right hand side becomes 0, so pkt of alpha k is clearly 0. So if pkt of alpha k is equal to 0, then again reapply the previous observation. Then we say that any polynomial would conduct alpha k into wk minus 1 if and only if the image is 0. So this typically means that wk minus 1 intersection the T cyclic subspace generated by alpha k. That is, if you choose an element from here, if that is to be inside wk minus 1, then that needs to be 0, right? Which is direct from the observation we had. So that means this is only the 0 subspace. Clear? Okay. So that means these alpha k's are the vectors such that V is a direct sum of W naught, which is a property admissible subspace of V, and the T cyclic subspaces generated by each of these alpha k's, k ranging from 1 to R. Okay. So therefore, what we have is basically, therefore, alpha 1, alpha 2 till alpha R define the same sequence of subspaces W1 till WR, let's say, which we had in the previous. WR is essentially equal to V. These subspaces comes from step 1, as do the vectors beta 1 to beta R. The only difference being that here we have the concept of independence. Okay. So and the T conductor Pk, which is the T conductor of beta k into wk minus 1, holds the maximality property. From step 1. Clear? What is the only difference? These vectors have an additional property that so we have the additional property that W naught Z alpha 1 T and so on till Z alpha R T are independent. Clear? Now we already have this in fact that pk of alpha k is 0. That happens for all. Further, pk of pkt of alpha k is 0 for all k. Therefore, just equating zeros on both sides, we can write this as pkt of alpha k can be written as 0 plus p1t of alpha 1 plus p2t of alpha 2 and so on till prt of alpha r. Right? Sorry, I should write it not like this. I should use that. Yeah, pkt of alpha k. Yeah, this is correct. Yeah, we should use till, yeah, k minus 1. Right? Pk minus t alpha k minus 1. Correct? Yeah. Now this is correct. Okay. So then from step 2, pk must divide pk minus 1 for all k ranging from 2 to r. Right? Clear? Because pk will divide each of these p's. Yeah, so it's obvious. Okay. So then from step 2, pk divides pk minus 1, and so we have already got those vectors which satisfy the statement 1 and statement 2 of the cyclic decomposition theorem. So now we have only one step left, which is step 4, which deals with the uniqueness of the integer r and these t annihilators, because pkt is a t annihilator of alpha k, right, for all k. So so basically we need to establish the uniqueness of r and the uniqueness of these t annihilators. Okay, so that's step 4. We show the uniqueness of pk, uniqueness of r, and all the pi's. Okay. Now how do we do this? So first thing first, to show uniqueness, we need to assume another set of vectors which obey the conditions 1 and 2 of the cyclic decomposition theorem. Okay. So suppose in addition to the vectors, to the non-zero vectors, alpha 1, alpha 2 till alpha r, there exists non-zero vectors, say gamma 1, gamma 2 till gamma s, with respective t annihilators, g1, g2 till gs, such that statement number 1 of the cyclic decomposition theorem, to be very precise, that V is a direct sum of W naught. W naught is a property admissible subspace of V. So it's cyclic subspace generated by gamma 1. So on the T cyclic subspace generated by, we have gamma 1, we have here gamma S, and number 2 is that the GI's should divide GI minus 1 for all. Okay, I is equals to 2 to S. Clear? So to show, for uniqueness, what we need to show? We need to show that R must be equal to S and each pi is equal to gi, right? Or I should say each pi, for all I is equals to 1 to R. I can use the index R now because I have already stated that we must show R equal to S, right? First thing we show is that P1 is equal to G1. We show first P1 is equal to G1. How do we do this? Now, the polynomial G1, it can be determined from these statements, right? So suppose I name this set of statements A. Okay. So G1 can be determined from A as the T conductor of V into W naught. Okay. So what do we do is basically define SVW naught to be the so it is the collection of polynomials f such that ft of v is in W naught for all v in the vector space. Clear? Clear? So this is an ideal. This is an ideal of the polynomial ring. Hence, it has a unique monic generator, and that generator is clearly G. Right? What we need to show is that the polynomial G1 is determined from A as the, or I should write this statement at the last. Let me not use this for the moment. So basically what happens is that, so I can also use this sort of a definition that this set consists of those functions such that the range of f of t is inside W. Clear? So obviously it's a non-zero ideal and non-zero ideal of the polynomial algebra fx. So f is the underlying field of V, for example, or I should hold that as a fact, and so it should have a unique monic generator. We will clearly show that G1 is the unique monic generator. Yeah. What we do is that if I choose a vector beta from V, let beta be in V, then beta will clearly have the form beta naught plus f1t of gamma 1 and so on till fst of gamma s. This comes from 5, right? Then from 5 we have this. Clear? Then what is g1t of beta? So it's g1 t of beta naught plus summation over I is equals to 1 to s g1t fit of gamma I, right? Now gi divides so now gi divides g1, right? Because gi divides gi minus 1 for all I is equal to 2s. So gi will clearly divide g1. Gi is the t annihilator of alpha I. So G1 will also be the t annihilator of alpha I. So that implies G1t of alpha I, sorry, gamma I, I'm very sorry, gamma I must be equal to 0 for all I, right? And if G1t of gamma I is equals to 0 for all I, and then G1t of beta naught, so it must be in W naught, right? So now G1t of beta naught will be, sorry, let me just write it like this, and then so if so this part completely becomes 0, right? This part completely becomes 0, and then we have G1t of beta is equal to G1t of beta naught. This is equal inside W naught, because W naught is a property admissible subspace, so it's basically a T invariant subspace as well. So G1t of beta naught is inside W naught because beta naught is inside W naught. And then G1t of beta is equal to G1t of beta naught. So G1t of beta is inside W naught, right? So this means that G1 is inside the T conductor of V into W. Clear? Because beta was an arbitrary element from V, right? But G1 is the monic polynomial of least degree, which sends gamma 1 into W naught, right? But G1 is the monic polynomial of least degree. Now obviously see, G1 is the T annihilator of gamma 1. That means G1, so G1 is the least degree monic polynomial such that G1t of gamma 1 is equal to 0. 0 is obviously inside W naught. So G1 is the least degree monic polynomial such that G1 sends gamma 1 to 0, which is an element of W naught. So G1 is the monic polynomial of least degree which sends gamma 1 into W naught, right? So that means G1 is the monic polynomial, and that's again obvious because the other GIs you have, they will all divide G1. So their degrees are obviously, so what I'm trying to say, so we are concerned with gamma 1 sending it to W naught, right? G1 was the T annihilator of gamma 1. So it's the least degree monic polynomial which sends gamma 1 to 0 under T, right? So therefore G1 is the monic polynomial of least degree which sends gamma 1 into W naught. It's obvious, right? So that so it's the monic polynomial of least degree in SVW naught, right? Clear? That means it generates SVW naught. Clear? So, so therefore G1 is the it's the least G1 is the monic polynomial of least degree in SVW naught. So indeed it's the generator of W naught of SVW naught. So it's an ideal. It contains a least degree monic polynomial which generates SVW naught. G1 is the monic polynomial of least degree inside, so it will generate SVW naught. Further, or I should say analogously, replacing G1 with P1 and applying the above steps for the vectors alpha I, we will get the same result, right? We get P1 generates SVW naught. The generator must be unique, so this will imply G1 is equals to P. Clear? So we have successfully showed that G1 is equal to P. Okay. Now we are left to show the other part, that this holds for every GI. How do we do that? First, we consider these three set of statements. You can consider them as an exercise and prove it later, but these statements are very trivial and very simple. Just consider them as tools. So tools. Number one, let's say if f is a polynomial, then number one is that if ft of the T cyclic subspace generated by alpha, ft of this whole image is equal to T cyclic generated by ft alpha. We denote, let me just use this notation, that we denote ft of w is a subspace, to be the collection of these elements, ft of w, such that w in set capital. Clear? So ft of this subspace is exactly equal to zft alpha of t. Number two says that if v can be written as v1 direct sum v2 so on till some vk, such that each vi is t invariant, then ft of v is equal to ft of v1 plus direct sum, ft of v2 so on till ft of vk. And number three is that if two vectors alpha and gamma have the same p annihilators, then ft of alpha and and ft of gamma, these two vectors will also have the same t annihilators. Will have same t annihilators, and hence that proves that dimension of the t cyclic subspace generated by ft alpha is same as the dimension of the t cyclic subspace generated by ft gamma. Okay, so these are the three tools we would use. Okay. Now let's come back to the proof. Coming back to the proof. What we do is we choose r to be greater than equal to 2. Okay. If r is greater than equal to 2, then dimension of W naught plus dimension of the t cyclic subspace generated by alpha 1, this must be less than dimension of V, right? Clear? Now, since P1 is equal to G1, therefore dimension of the t cyclic subspace generated by alpha 1 should be equal to the dimension of the t cyclic subspace generated by gamma 1. P1 is the t annihilator of alpha 1, G1 is the t annihilator of gamma 1. So that would imply the dimension of W naught plus the dimension of Z gamma 1 t is also less than dimension. So that will obviously imply S must be greater than equal to 2s, because we need more t cyclic subspace in order to reach the dimension of V. Hence, we need more than or equal to 2 index S. Clear? So if I have R greater than equal to 2, I have S greater than equal to 2. Therefore, it's obvious to ask the question. So it's obvious to ask the question if P2 is equal to G2 or not. Okay, because if P2 is equal to G2, if so, then we have established an induction. And hence a proof. So we just need to show that P2 must be equal to G2. That's it. Okay. So how do we do this? Now we have two decompositions of V. Okay. What are the decompositions? Let me just come to it. So we have one of the decomposition is V is equal to W naught plus Z alpha 1 t direct sum, and so on till Z alpha R t. If I apply P2 on it, so that means what is P2t of V? So it's P2t of W naught plus, now P2t of Z alpha 1t is same as from 1. It's same as the t cyclic subspace generated by P2t of alpha 1. Right? Now P2 is the, or let me just write it. Plus you have Z P2t of alpha 2 t, and so on till Z P2t of alpha R, right? Yeah, so this happens from the tool 1. Now observe, but P2t of alpha 2 is 0 because P2 is the t annihilator of alpha 2, and Pk divides P2 for all k greater than 2, which implies P2t of alpha k is equal to 0 for all k greater than 2. If you include this, then all k greater than equal to 2. So that means that this part completely vanishes, because the t cyclic subspace generated by the 0 element is simply the 0 subspace, right? So that implies P2tv is same as P2T of W naught, direct sum the T cyclic subspace generated by P2T alpha 1 and, right? Is it clear? Similarly, another decomposition by the other decomposition, which was in terms of gamma, the vectors gamma, we can write P2T of V as P2T of W naught, direct sum the T cyclic subspace generated by P2T of gamma 1 and so on till the T cyclic subspace generated by P2T of gamma S, right? I guess this part is completely clear. So I name these two set of statements as, let's say, okay. Now um, obviously what does this 2 imply? Okay, okay, observe that P1 is equal to G1, right? Or we can think of it in this form. Yeah, observe that P1 is equal to G1, that is alpha 1 and gamma 1 have the same T annihilators, So using tool number 3, we can say that if you choose any polynomial f, then the dimension of the T cyclic subspace generated by ft alpha 1 should be equal to the dimension of the T cyclic subspace generated by ft gamma 1, right? So we can choose that polynomial to be P2. Therefore, from tool 3, we can say that the dimension of the T cyclic subspace generated by P2 alpha 1 is equal to the dimension of the T cyclic subspace generated by P2T gamma 1, right? Therefore, from B, it's clear that the dimension of all the other subspaces are equal to 0, because dimension of this plus dimension of this equals dimension of this, being a direct sum, and dimension of this and dimension of this come out to the same, dimension of this and are already same. So all the other dimensions, they should equal 0. Therefore, from B, it's clear that dimension of the T cyclic subspace generated by say P2T gamma I, this should be equal to 0 for all I greater than equal to 2, right? Or we can say that means that P2T of gamma 2 is equal to 0, right? But G2 is the T annihilator of gamma 2, so that means G2 divides P. Right? Why does this happen? Because G2 is the T annihilator of gamma 2. Clear? But obviously we can reverse these statements, right? Reversing these statements for P2 in place of G2 and the vectors alpha i's in place of beta in place of gamma i's, we get P2 divides G2. What I'm trying to say is that if I use the sort of notation of this, so if I do not use P2 here, instead I use G2 in this case, okay? Then if I use G2 in this case, then this statement is for the vectors, okay, one sec, let me just revert this part, yeah. So then this statement holds for the vectors alpha 1 to alpha r, and this statement holds for the vectors gamma, hold for only the vector gamma 1. So proceeding, we will simply get that G2 of alpha 2 is equal to 0, right? Because proceeding we get G2 of alpha 2, G2T of alpha 2 is 0. So, but P2 is the T annihilator of alpha 2, so that would mean P2 must divide G. Is it clear? So P2 divides G2. So these two imply, that implies P2 is equal to G2, and that's the, okay. Yeah. So let this lecture be up to this much. In the next lecture, we will be coming up with more concepts regarding cyclic decomposition theorems, and the next lecture, we will be introducing the concept of a rational form of a matrix. Okay. So meet you guys in the next lecture.